So let's continue with bounded functions. Let x be a member of the closed interval AB. Now a function f is said to be bounded above if there exists a real number, say capital M, such that f of x is less than or equal to capital M for all x be a member of the closed interval. Again, a function f is said to be bounded below if there exists a real number, say small m, such that f of x is greater than or equal to small m for all x be a member of the closed interval. So what this primarily means is that for a function to be bounded above, f of x should be less than or equal to capital M, and for a function to be bounded below, f of x should be greater than or equal to small m. Now to clearly understand these two statements, let's try to solve this question. So question 1. Given that the function f of x is equal to x squared plus 5 defined on the closed interval 0, 1. Now the first thing we are going to do is to try and get the domain of this function. Now the domain of this function is what has been given in the question as the closed interval. So that is the closed interval 0, 1. This is the domain of the function. The next thing is to determine the range of the function, and that is given by the image of the elements in this interval with respect to the function f of x. So basically we don't need all the elements in this interval, we just need a few of them, and probably we are going to use 0 and 1. So the image of 0 with respect to this function is given by f of 0 equals, now in place of x we are going to substitute 0. So we have 0 squared plus 5, and that is equal to 0 plus 5, and then that is equal to 5. Now for f of 1, that is equal to 1 squared plus 5, and then we have 1 plus 5, and that is equal to 6. Therefore the range of this function, that is given by f of x equals the closed interval 5, 6. So now how do we determine the upper bounds, the least upper bound, lower bounds, and the greatest lower bound? Now let's represent this interval on the number line. So we have negative infinity, positive infinity, 5, 6. Now because this interval is closed at both ends, we are going to represent this by a shaded circle, and this is the interval, that is the closed interval 5, 6. So to find the upper bounds of this interval, the upper bounds are defined as the numbers that are greater than or equal to the highest element in the interval. Now the highest element in the interval is 6. Therefore the upper bounds are going to be numbers greater than or equal to 6. And then numbers greater than or equal to 6 are 6, 7, 8, 9, and so on and so forth. So we say that the upper bounds are 6, 7, 8, 9, and so on and so forth. Now out of these upper bounds, which of them is the least? So the least upper bound is equal to 6. Out of these numbers, 6 is the least. Now to the lower bounds. So the lower bounds are said to be the numbers that are less than or equal to the least or the lowest number in the interval. Now the least or the lowest number in the interval is 5. Therefore numbers less than or equal to 5 are 5, 4, 3, 2, and so on and so forth. Therefore the lower bounds are 5, 4, 3, 2, and so on and so forth. And out of these numbers, the greatest of them is 5. Now we need to understand that a function that has upper bounds has a least upper bound, and a function that has lower bounds has a greatest lower bound. And also, a function that is said to be bounded above and bounded below is said to be a bounded function. Now, this function, that is the function f of x equals x squared plus 5, has upper bounds and then lower bounds. Now, since it is bounded above and then bounded below, we say that this function x squared plus 5 is a bounded function. Now, let's take another question. So, for example 2, we are going to determine the upper bounds, the least upper bound, lower bounds, and the greatest lower bound of this function f of x equals 1 over x for the interval, or for the closed interval 0, 2. Now let's try to solve this question. So first of all, let's determine the domain of this function. Now, fixing 0 into this function, you realize that when you fix 0 into this function, you have 1 over 0, and that is undefined. Now, since 0 or fixing 0 into this function is undefined, it means that 0 cannot be part of the domain of this function. Therefore, we are going to represent that with an open interval 0 and then a closed interval 2, because apart from 0, all the elements in this interval make the function f of x defined. So this is the domain of this function. Now, to find the range of this function, we are going to find the image of 0 and 2 with respect to f of x. So first, let's have f of 0. So that is 1 over 0, and that is undefined. This is undefined. Now, even though this expression is undefined, when you have such an expression like this, the limit of this expression as x approaches 0 is infinity. Now, as x becomes very smaller and smaller, and thus close to 0, this value becomes very large and thus approaching infinity. Now, since we do not have any definite value for infinity, we say that this function does not have upper bounds. Now, if the function does not have upper bounds, then it means that it has no least upper bound. So it means that this function has no upper bounds and thus has no least upper bound. Now, to f of 2, so f of 2 is equal to 1 over x. In place of x, we have 2, and this is the same as 0.5. So the range of this function, f of x, is giving us the closed interval 0.5, comma, open interval plus infinity. Now let's represent this on the number line. So we have this negative infinity, positive infinity, and then we have 1 over 2 here, and 1 over 2 is part of the set because we have a closed interval on the left. So that's going to be to the right, so including 1 over 2 and then to the right through to infinity. Therefore, since infinity is not a definite number, we say that there are no upper bounds. So for upper bounds, we say that no upper bounds, and then for the least upper bound, we have no least upper bound. Now for the lower bounds of this interval are going to be numbers less than or equal to half. So numbers less than or equal to half, we can have half, 0, negative half, and so on and so forth. So the lower bounds, we have 1 over 2, 0, negative 1 over 2, and so on and so forth. And out of these lower bounds, the greatest of them is half. Now, since the function f of x, which is equal to 1 over x, is only bounded below and not above, it follows that f of x is not a bounded function. F of x is not a bounded function. Now let's move on as we discuss the monotonicity of a function. So let S be an interval, that is the closed interval AB, and x1 and x2 be members of this closed interval such that x1 is less than x2. Now a function f is said to be monotonically increasing on the interval if f of x1 is less than or equal to f of x2. And if f of x1 is less than f of x2, then the function is said to be strictly increasing. On the other hand, a function f is said to be monotonically decreasing on the interval if f of x1 is greater than or equal to f of x2, and if f of x1 is greater than f of x2, then we say that that function is strictly decreasing. Now a function is said to be non-monotonic if it increases or decreases for some time and shows opposite behavior at a different location. Now one way to determine whether or not a function is monotonically increasing, decreasing, or non-monotonic is the fact that let's suppose that we have a function. Suppose that we have a function f which is continuous. That function is continuous. It's continuous on the interval, that is the closed interval AB, and differentiable on the open interval AB. So let's suppose that we have a function which is continuous, and that is continuous on the closed interval AB and then differentiable on the open interval AB. A. Now this function is said to be monotonically increasing if the first derivative of that function is greater than 0 for all x in the open interval AB. B. The function is said to be monotonically decreasing if the first derivative of the function is less than 0 for all x in the open interval AB. Now, as usual, the function is non-monotonic if it increases or decreases for some time and shows opposite behavior at a different location. So that is what we mean by a non-monotonic function. Now let's try a few examples. Question 3. Show that the function square root of x minus 2 is an increasing function on its domain. So let's try to solve this question together. So we are given the function f of x equals the square root of x minus 2. Now the first thing we need to do is to find the domain of this function. Now, because we are working under real numbers, the value under the square root should be greater than or equal to 0. Now the moment we have a negative value under the square root, then we move on to complex numbers, which we are not dealing with or which we are not focusing on. Our focus is on real numbers. Therefore, this value should be greater than or equal to 0. Therefore, for that matter, we say that the function, that is the square root of x minus 2, should be greater or equal to 0. Now at this point, we are going to remove the square roots. So we square both sides of the equation, square cancel square roots, and we are left with x minus 2, and that is greater than or equal to 0. At this point, you transpose negative 2 to the right hand side. You have x is greater than or equal to 2, and this happens to be the domain of the function. That is, x is such that x is the set of all real numbers x is greater than or equal to 2. So the domain of the function is the closed interval 2, open interval, positive infinity. This is the domain of the function. Now, to show that this function is an increasing function, we say that a function is said to be monotonically increasing if the first derivative of the function is greater than 0 for all x in the open interval AB. Now in this case, we have the open interval going to be 2 positive infinity. So what we mean to say is that this function is an increasing function if the first derivative of the function is greater than 0 for all x in this open interval. So first of all, let's try to find the derivative of this function. So we have f of x to be equal to the square root of x minus 2, and that can be represented as x minus 2 all exponent half. Therefore, the derivative of this function becomes, now we are going to drop the exponent, so that becomes 1 over 2 times, we differentiate what's in the bracket, derivative of x with respect to x is 1, and then this one is a constant, so when you differentiate a constant, it becomes 0, and then you repeat what's in the brackets, and then you subtract 1 from the exponent. Now 1 over 2 minus 1 is negative 1 over 2. Now let's simplify this. So we have 1 over 2 times, this becomes 1 over x minus 2 or exponent 1 over 2, and then finally we have 1 over 2 times 1 over the square root of x minus 2, and that is for all x in the interval 2 plus infinity, that is the open interval. Now we are going to put values of x in this interval to see if the derivative of this value or of this function is going to be greater than 0. Now if we put 3 here, so because this is an open interval on the left, we are not going to put 2 inside because 2 is not part of the set. So starting from, let's say 3, if you put 3 here, you have 3 minus 2, which is 1, and then because you have a positive value, everything here becomes positive, that is greater than 0. Let's say you put 4 inside of here, 4 minus 2 is still positive, everything becomes positive, and that's greater than 0. If you put 5, 6, and so on and so forth, everything you have here becomes positive. Therefore, we say that since the first derivative of the function is greater than 0 for all x in the open interval 2 plus infinity, f of x is an increasing function. It's an increasing function. Now we can also use another method to verify that f of x is indeed an increasing function. So let's do that together. Now we said that for a function to be an increasing function or a monotonically increasing function, for x1 is less than x2, f of x1 should be less than or equal to f of x2. So that is the condition. Now let's see if we are going to satisfy this condition for this function. So we have f of x to be equal to square root of x minus 2. Therefore, f of x1 means that in place of x, we are going to have x1. So that is x1 minus 2, and then f of x2 also means that in place of x we are going to have x2. Now x2 is considered to be the next term after x1, so instead of having x2 we are going to have f of x1 plus 1, and that is equal to, wherever we see x in the function we are going to replace that with x1 plus 1. So we have x1 plus 1 and then minus 2. So we have f of x1, that is square root of x1 minus 2, is less than or equal to f of x2 square root of x1 plus 1 minus 2. Now let's simplify this. So on the left hand side we still have x1 minus 2, that is the square root of x1 minus 2, less than or equal to square root of x1. Now 1 minus 2 is negative 1. At this point, let's square both sides to remove the bracket. So doing so, we have x1 minus 2 is less than or equal to x1 minus 1. Now let's transpose x1 to the left hand side. So we have x1 and then minus x1 minus 2 is less than or equal to negative 1. So x1 minus x1 is 0, so it goes away. We have negative 2 is less than or equal to negative 1. Now since negative 2 is less than or equal to negative 1 is a true statement, it means that our initial assumption that f of x1 is less than or equal to f of x2 for this function is true. Therefore, f of x is an increasing function. Let's try another question. So to question 4, consider the function f of x equals x over x plus 1 in the interval 0, 1, and then investigate the following properties of the function: a, boundedness, and then b, monotonicity. So let's try to solve this question together. This happens to be the last question for today's lesson. So we are given the function f of x, and that is equal to x over x plus 1, and then we have the interval. The interval is 0, 1, so probably this is the domain of the function. Now we are going to investigate the following properties, that is a, boundedness, and then b, monotonicity. So a, boundedness. Now a function is said to be bounded if it is bounded below and above. Now let's try to find the image of the element in this interval with respect to this function. So basically we are going to use 0 and 1. So f of 0, for f of 0 we have 0 divided by 0 plus 1, that is 0 in place of x. So we are going to have 0 divided by 0 plus 1 is 1, and then 0 divided by 1 is 0. And then for f of 1 we have 1 over 1 plus 1, and that is equal to 1 over 2, so we have half. Therefore f of x, that is the image of this function, is going to be the closed interval 0, half. Now let's represent this on the number line. So this is 0, closed, and then half, also closed. So this is the interval we are talking about. Now this interval is bounded above by 1 over 2, 1, 3 over 2, 2, and so on and so forth. So if we are talking about the upper bounds of this interval, we are going to talk about numbers greater than or equal to half. So half, 1, 3 over 2, 2, and so on and so forth. Now, for the lower bounds, this interval is also bounded below by 0, negative half, negative 1, and so on and so forth. So 0, negative half, negative 1, and so on and so forth. So the lower bounds are basically numbers that are less than or equal to 0. Now, since this function is bounded above and below, we say that since f of x is bounded above and bounded below, it is a bounded function. It is a bounded function. Now let's move on to B, the monotonicity of the function. Now we said that a function is monotonically increasing if for x1 is less than x2, f of x1 is also less than or equal to f of x2. Now at this point, we don't know whether the function is an increasing function or a decreasing function, but let's assume that this function is an increasing function. At the end of time, if we realize that the function is a decreasing function, then we can make changes to it. But as it stands, let's assume that the function is an increasing function. So if we have an increasing function, then this is the argument that for x1 is less than x2, then f of x1 should also be less than or equal to f of x2. So we have the function to be f of x equals x over x plus 1. Therefore, f of x1, that is in place of x, we have x1. So we have x1 divided by x1 plus 1. And then for f of x2, that's going to be x2 is equal to x1 plus 1. So we are going to have x1 plus 1 divided by x1 plus 1 plus 1. Now 1 plus 1 is 2, so that becomes x1 plus 2. Therefore, since f of x1 is less than or equal to f of x2, it follows that x1 over x1 plus 1 should also be less than or equal to x1 plus 1 over x1 plus 2. Now let's cross multiply. So we have x1 into brackets x1 plus 2 less than or equal to x1 plus 1, and then x1 plus 1. Now let's multiply across. So x1 times x1 is x1 square, x1 times 2 is 2x1 less than or equal to x1 times x1 is x1 square, x1 times 1 is x1, 1 times x1 is also x1, so that becomes 2x1, 1 times 1 is 1. Now let's transpose x1 squared and then 2x1 to the left hand side. So we have x1 squared plus 2x1 and then minus x1 squared minus 2x1 is less than or equal to 1. So x1 squared cancels out negative x1 squared, 2x1 cancels out negative 2x1. So we are left with 0 is less than or equal to 1. Now since this statement is true, it follows that our initial assumption is also true. Therefore, the function f of x is monotonically increasing, hence f of x is monotonic.